Good afternoon, everybody.
Hello.
Hello. Let me just check. Okay, there's no one in the waiting room, stuck in waiting. Okay. So yes, we do have a lecture today, right? Because vacation starts tomorrow according to the schedule of the term given on the internet page of the university. So I also want to continue the lecture sort of as fast as possible because the exam will be very close to the end of the lectures. So we can finish early, right? So you have enough time to do your preparation. Okay? So I don't wanna miss the chance to proceed in what we want to do. Okay, so what you see here is the table of content of chapter 4. So just briefly go through the points we already covered. So we started with a network, a one-layered network, and the activation function of the neurons are linear. Then we briefly introduced the sorts of HAP and the observations HAP made and what this means for learning. And I also briefly covered the molecular basis of it, but this was years after HAP described this learning, right? So that biologists found that this is actually going on in the brain. So we went on to the math, and the plain Hebbian learning rule is unstable. I presented you a proof for that, right? Which involves, again, another mathematical topic like differential equations and systems of differential equations. But just to show you that there is a reason why this is unstable, and you can show it mathematically. So we had a problem. And then we started to solve this problem by doing implicit normalization of this plain Hebbian learning rule, a normalization step. So the weight vector was not able to diverge during the training process. And this involved several steps to come up with Oya's learning rule. This was a learning rule where we just focused on a single neuron. But there is a generalization to Oya's learning rule that can be applied to all the neurons in the linear layer. And this is called Sanger's learning rule. It's a bit more complicated, and I don't want to go into depth how you come up with Sanger's learning rule. Okay? So then we moved on and we analyzed Oya's learning rule. So because it's an unsupervised learning rule, so we are definitely not fitting target data, the labels. So, but what do we learn? And this was part of the next two subsections, to analyze what we are learning. And what we found is that basically the learning rule solves an eigenvalue problem for the covariance matrix of our data. And we've been into the interpretation of the learning rule. So what does it by us doing this eigen decomposition of the covariance matrix, right? I think we managed to finish this part by looking into the learning algorithm. I'm a bit unsure. Did we do that?
Professor Vorlesung, can you please repeat the question?
Have you seen the structogram of the learning algorithm? I forgot. I know we stopped somewhere around it, but I forgot. I think we've done that.
We look at the structogram from the Heppian learning, and from the OYA, we don't look at this.
Yeah. Okay. So let's jump in there. So we jump in there, and I'm not sure. Okay. Can you tell me, what do you see? You still see the table of contents, is that right?
We currently only see you.
Yes.
Okay. So, good. What do you see now?
Now we see the table of content.
Table of content.
Yes. Now we see you.
Yeah, I know. As you probably recognized, I mean, starting in the morning, I do have actually problems sharing my screen, and I don't see all the windows. So it doesn't show me all the windows that are currently active. So I'm a bit struggling at the moment.
The problem we have it also at the morning too. We have problems.
Yeah, so it started. I mean, it started yesterday, today.
Yeah.
The problem. This is a technical problem. I don't know. I don't do anything different from what I did the previous lectures. So let's try. Nope. So what do you see now?
The table of contents. Yes.
Still table of content?
No.
I see the PowerPoint.
Yes.
Now you see the slides, the regular ones, right?
Yes.
Yes, fine. Okay, so we were analyzing. This is the part, right? So where we talked a bit. I mean, we also talked about how to calculate these covariance matrix, right? This is technique. Have you done that? Yeah, we've done that, right? So I remember that I was explaining this slide.
Yes, you already had.
Yes. So I'm asking, is there someone who can explain what's going to happen or what's happening? I mean, what these two plots basically express? I move on. Okay. Have you done that? Briefly, maybe. I'm not sure. Okay, let's start here. So basically, what we are doing, we are calculating weights. This is a weight matrix, right? So the columns of the matrix are the weights of the neurons in the layer. So when we transpose this matrix and multiply it with an input value, we get an output vector, a new representation Y of this, the original input data X. So on the left, in the left plot, we see our data. It's a cloud. It's a distribution of data in input space, X1, X2. right? So, okay. So, and this is the normal, orthonormal basis of two-dimensional space. Okay. So if we feed these input patterns into this linear network and do the learning, the training, right? What we end up with are new representations for all these black dots here, right? So we get vectors y. And if we look at the distribution of the vectors y, right? We do see, and now you have to rotate this in your brain, right? So we have new axes, right? The y coordinates are now along the axis of the first and the second. This is a typo. This is W2 of the eigenvectors. Okay. So what we do by this transformation, we are rotating space. So we are rotating E1 and E2 onto W1 and W2. Okay, and as you can see, the Y1 coordinate, along the Y1 coordinate, we now see the maximum spread of our input distribution. Yeah, and orthogonal to it, we have the dimension with the minor scattering of the data. Okay. And here we do see a clear correlation between X1 and X2, right? There is a correlation, a covariance. When we look here at this cloud and we look in the Y1 and Y2 coordinates, right, we don't see any correlation or covariance. Okay, so the outputs yi, as it says here in the note, they are uncorrelated. That's what we are gaining. Are there any questions?
Professor, can you repeat again how they are uncorrelated? Means I did not get it.
So correlation means that when you double x1, there is something predictable going on with x2.
Okay.
Okay. So basically, if you increase x1, x2 will increase. Do you see that?
Yes.
Okay. So if we increase y1, right, there is no systematic increase in y2.
Okay. I got it. Okay.
You're right?
Yeah.
You're on board? Okay. Okay. So summarizing the learning algorithm. So this is Senger's learning rule that we apply to the neurons in our layer. Neuron 1 to neuron I. I is a number we can choose. I is smaller or equal to K, and K is the dimension of input space. So I is basically the dimension of the output vector of the output vector of the linear net of the Y's, right? Okay, so this is the learning rule, and this is the algorithm, yeah? So we have an initialization, yeah, as we had already for the perceptron and the ADA line. So we have to initialize all our weight vectors of these I neurons. We do this randomly, but we make sure that the norm of all these weight vectors is equal to 1. So from practical point of view, you are initializing your weights of all the weights of all these neurons. The weights also includes the bytes, honestly. Okay. So, and then you normalize the weight vectors by dividing each weight through the norm of the complete weight vector. Okay. This is technically quite simple. We have to choose a learning rate. alpha. And as you can see, this learning rate is small. It's positive and small. And we have to initialize our iteration counter. So because we learn example by example, right? So we are doing this from one iteration to the other. The first step in this learning loop, while loop, right, is what we do. We choose one particular pattern from our input, from our training data, xn. Yeah. And then we do for all our neurons, we are computing first of all the current output value of the neuron for the chosen input pattern data point. Okay. Then we calculate the delta Wi for the weights of this neuron. So, and this is basically the part that's after the alpha here, right? This is the delta W. So we take the output of the neuron, we calculate the difference between xn and the sum over a product of the output of the other neurons with the weight vector. Okay. And then we compute a new weight vector for each of the neurons, right? So this is a loop. This is a for loop. Okay, so we do this for all the neurons, and we do this from starting from neuron 1 to neuron I, because when you look at the sum here, so we are successively subtracting the dimensions that have been already covered by neurons that have an index lower than the current one. Okay. Okay, and then we are increasing our iteration counter, and we continue to do this. We talked about, okay, since we don't have target values, we don't have an error. We can't say, okay, if the classification error is 0, we are done, right? Or some sort of criteria like that, because it's an unsupervised learning. So we have to have another criteria. And one interesting thing or one thing we can do, we can observe how the weights change from one iteration to the other. So if there is some degree of change, so we define some small value, epsilon, right? Which we consider to be an insignificant change in the direction of the weight vectors. And we repeat these learning loop till for all the neurons we don't see changes in the weight vector that are higher than this epsilon. It's a bit loosely formulated here because usually you have to observe this change, the mean change of the weight vector over a couple of iterations. Then this criterion becomes much smoother. All right. So this algorithm looks a little bit more complicated than the perceptron learning algorithm, but in principle, the structure is the same. All right, we have here a loop because we have now to consider more than one neuron. So we have to learn in more neurons. Questions? All right.
Professor, this learning rate, it is determined randomly, or some functions is there to determine this learning rate that is positive and near to 1?
Okay. so we've seen some of the analysis that you have to do when you develop such a learning rule, right? I mean, it's not like you think of a learning rule and then just program it and look what happens. So you have to analyze, what do you do there? What are the constraints and so on? So we linearized, or we did use this OYA learning rule, which is a local learning rule, which you want to have for learning, because you don't want to be dependent on the results of other neurons, because that makes problems in the update. So there's also analysis possible, because we've done some approximation there when we did that, and you can look at the convergence radius of this approximation, because we do a Taylor expansion, right? And there is a convergence interval given for this expansion. And so you can deduce an upper bound for this learning rate where it's guaranteed that the learning rate is stable. But I don't want to do the math for that. Yeah? Okay.
Thank you.
Did you understand the point that I'm making?
Yes.
We do an expansion. We approximate this the learning rule. So we neglect a lot of things, right? By doing that.
Yes.
And so we do this expansion especially. And so we can analyze the radius of convergence, because we do the expansion around a point of alpha 0 equals to 0. So what's clear is it has to be a small learning rate. But the bounds for the stability of this expansion, the convergence guarantee, this is another bit of math you have to do. But there is this upper bound, okay? So this is the first remark on the next slide. There exists an upper bound for the learning rate alpha, which guarantees convergence of the learning rule.
Okay.
That's an upper bound. So up to this bound, the learning rate is the learning rule is guaranteed to converge. Yeah, it's stable. There is an annotation here. There may be stability outside this upper bound, but it's not guaranteed. Okay. Because it's again an approximation. Yeah. So there is another problem, because these eigenvectors are directions in space, right? And depending on the starting values that you choose, you will end up either with a solution with Wi or minus Wi. That means, so either you are in the positive direction or in the negative direction. The direction of the vector is the same. It's just the sign. Okay, because that depends on the starting values that you choose. We will see this later on in the simulation. Okay. Of course, we are solving an eigenvalue problem. And we are solving an eigenvalue problem, and there are a lot of alternative numerical methods how to compute eigenvalues and eigenvectors of a covariance matrix. Right? There are methods that calculate the roots of the characteristic polynomial first and then calculate the eigenvalues. That's roughly the same what we did in the mathematical background exercise. But there are other numerical methods that are calculating the eigenvalues different. For example, you have so-called basic rotations, like elementary rotation matrices, and you can compose the complete rotation matrices for symmetric matrices, the diagonalization by successively approximating it with this elementary relations. Well, all kind of fancy numerical methods how to calculate eigenvalues and eigenvectors of a given matrix. And depending on the characteristics of the matrix, whether it's symmetric, whether it's positive definite or so, you have special methods, okay? No doubt about it. But all these methods require that you are calculating the covariance matrix prior to applying the method. The advantage of the neural implementation of this is that, for the one hand, since we have pattern-based learning, if we get more training data, right? If we have a process, a data generation process that delivers more and more training data, we can adapt online, right? So we can adapt our representation by just adding this training data and cycling over the training data a couple of iterations, and then we have the new representation. So this is called online learning, right? So we can online adapt to a changing distribution of input data. Okay, and another advantage is that we, at no point of the algorithm, we are calculating the covariance matrix C. Okay, these are the remarks in respect to the learning algorithm. I'm wondering now if we want to proceed. Okay, so we stop here. Before we move on with the slides, I want to do the second task on exercise sheet number 4. So as for the perceptron learning algorithm, we now want to watch the learning. Professor? And what's going to happen.
The screen is black.
I know, I'm not sure why.
Yes, this problem we have it also at the morning.
Yeah, but I'm going to change the slides anyway. So I'm now going to all right. Do you see the exercise sheet?
Yes.
Yes. So what we do now, we explore the properties of the learning algorithm. So again, I have a sort of hack, call it that way, a MATLAB hack, so which shows you what's going on, giving some synthetic data. So you understand what we are doing. So we are now looking at the learning algorithm, how it comes up with these principal components, these directions in space, and we also make some experiments concerning the stability of the algorithm. The interface you will see looks like this. So again, we have two input values, x1 and x2, right? So we are doing this with a data distribution in two-dimensional space. These are our training examples, and since we don't have classes now, they are all these x's, right? It's across. Okay, we don't have a separation between into different classes. Okay, so again, we have kind of parameters that specify the data. Currently, we do see 100 data samples, and they are drawn from a two-dimensional normal distribution with mean value at the origin, right? So the mean it's mean-centered data, and the scatter in the x direction is the variance is 0.5, and in the x2 direction it's 0.25. Okay, so we see this correlation between x1 and x2. And this is an angle. The angle basically, I mean, there's not because this is variance, there's no correlation involved in these parameters, but by rotating this distribution by some angle, we do see a correlation between x1 and x2. That's what I already tried to explain when we started the lecture for the two plots. So this is our data distribution. And we have the parameters of the learning algorithm. So the step parameter usually says after how many learning steps we look at the results, right? The results are displayed. So this is just a visualization parameter. Then we have alpha, and the alpha here is determined for the data set at hand. It's determined in a way that it guarantees stability. And this is our epsilon value that we are observing. Yeah, so we can change that. Okay, and what you also see here in the plot, you see the pre-calculated directions. These are the directions of the eigenvectors. They are orthogonal to each other and they are pointing in, this is the goal of our learning procedure, right? And they are scaled by the eigenvalue. So if it's a long vector, so the length of the vector determines or indicates the rank of the neuron in the layer. This is not quite, yeah, okay. And what we are now going to do is, first of all, we are testing the learning procedure using different rates of different learning rates alpha. Okay, we are changing this. So we look at it first as it's given, and then we look at what happens if we change the learning rate. And then we use a larger distribution, data distribution. We use 500 training points, and we do this again. Okay. I will show you now the program. Do you see the now Octave, or do you see the slides?
See Octave.
Okay. You do still see Octave? Okay.
Yes.
Okay. So you do see an additional window?
The additional window is black.
Still black?
Yes.
Okay. Better?
Now we can see it.
You can see, okay. So this is basically what I explained. So we do see the window now, right? So this is a slightly different data distribution. No, it's the same. Okay, so we will start with the settings that are given, right? So what we do, we start. By start initializes the learning algorithm. So we choose our weight vectors. This hasn't been a good starting point because, as you can see, the one direction is already almost the result of the learning. So I am Okay, this is much better. Okay. All right. So what you do see and okay. So now we do 100 learning steps. So we have 2 neurons, right? The weight vector of the first neuron is the blue one. The direction of the weight vector of the first neuron is the blue one. The direction of the weight vector of the second neuron is the pink one. Okay, and as you see, so the weight vector, both weight vector change. It's better observable for the blue one because it's longer. Okay, and what you can see now in the bottom, you can see the amount of change, yeah, that we had during the last 100 learning steps. Okay. So we already reached our epsilon. And as you can see, the direction of the blue weight vector is now in the direction of the numerically calculated eigenvector of the covariance matrix of that data. Okay, so we are basically done. We can continue, so you see the dynamics. So it's getting to fluctuate a bit, and yeah. All right. So okay. So this was our first try. We can redo that. All right, that's a good. Because now we have. So we do this again using different storing vectors. All right. So we are done. You can change that. Okay. So the situation we saw in these 2 simulations are, so there are basically 2 directions in space. This is W1 with positive sign, and if we multiply it with -1, right, we get the inverse vector pointing in the other direction. But the direction is still the same. So this was the second remark that we discussed. Okay, and it depends. Yeah, question?
I got a question. I got a question, and the parameter alpha, can I choose the parameter how I want?
No.
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 And
This is
why?
This is the upper bound. Yeah.
Yes, yes. And why I cannot choose alpha like I want?
To guarantee convergent behavior.
Okay.
Okay, we are going to change this now. That's the next thing we are doing. I just want to generate a starting condition where we end up in the direction, in the opposite direction, right? So it depends on the starting value.
I have an idea, because I think when I change alpha like I want, they stop the divergence. I think it's correct, and my weights.
The learning rule starts to diverge, right?
Yes, and my weights will be grow without control. Is this correct?
Right, and as when you remember, because we have an exponential function involved there, so
Yes,
if it starts to diverge, right?
Yes.
This is something like the coronavirus does. Okay.
Yeah.
It's going to really get rampant very fast. Okay.
Okay. Thank you.
But we will see this.
Yes. Thank you.
Okay, but now I have a starting conditions where we now will end up with exactly the optimal weight vectors given in black. Okay, let me show you this. Okay, so, all right. So the blue one now overlays the black one, but the purple, the pink one still is in the other direction. Moves towards the other direction. Okay. All right. Okay. So there is nothing more to say about it at the moment. So what we do now, I think it would be helpful if someone can tell me the change of the learning rates that we should consider. So I think one suggestion is to decrease learning rate by a factor of 10, right?
Yes.
All right. Okay. I'm trying to get. Okay, this is good. No, this is not good. Yeah, this is good. Okay. So we decrease the learning rate. Okay. This is very, very small learning rate. Oh, there's something wrong actually. I increased the number of learning steps after which we look at the results by a factor of 10 because I restarted. Okay, let's do that way. All right. Okay, so we can. Okay. I don't take the factor of 10, I now take a factor 2. Okay. So as you can see, when we decrease the learning rate, we make smaller steps. It takes much longer to move the weight vector towards the stable solution in the end.
Sorry,
Right?
can you repeat the last sentence? When you decrease the learning rates, what
We
happens?
make smaller steps in learning, so it takes longer. So the change of the weight vector per iteration is smaller.
Okay, that means when you change the alpha, it's the learning. It's I don't
How we
understand.
decrease alpha? We
Yes.
decrease, yeah,
Yes, you
a
decrease
factor
alpha.
of 10. All right. So this is one thing. So I had to increase the number of steps because the update in 100 steps is so small we can't see it. Okay, it would take ages till we see any change. So I doubled it. Okay.
Mhm.
Okay. So what's the next value in the list of alphas? Mr. Gottbani, do we have it? I mean, I can look it up. It's not a problem.
I just have a look.
It's so we checked 0.0.005. That's what we did.
Yeah.
Okay. So we already, when you remember, the initial learning rate was around 0.05, the upper bound. Okay. So what we do now, we are increasing from the upper bound by a factor of 10. So we're increasing beyond the upper bound. And we will watch what's going to happen. Do you still see the interface?
Yes.
Yes. Okay. Okay, so we do that. So we decreased by a factor of 10, and now we increased by a factor of 100, which makes a factor of 10 from where we started. Okay. So let's see what happens, and I'm decreasing the number of steps, again, after which we look at the current state of the weights. All right. So as you see, the steps are, honestly, I don't. Okay. I restarted. A big jump after 100 steps. Do you see?
Yes.
Okay. Compared to, all right. So it's now a bit fluctuating around because the updates are now increased by a factor of 10 in magnitude for each learning step. Okay.
Yes. Professor, I got a question. Is this what we see now? The uncontrolled.
No, this is still stable.
Okay. This is still stable. Okay. Okay.
Still stable.
Okay.
So because we are doing between each of the display steps, when you see a new weight vector,
Yeah.
100 learning steps. So 100 times we've updated the weights of the first and the second neuron.
Yes.
Okay, so this is still stable. Okay, we can go to 1.0. I'm now just, okay, so that's good. Okay, so I will decrease the number of learning steps, be a bit cautious. So we start learning. Okay. Again. As you can see, the oscillation around the right direction now becomes even more pronounced. All right.
Professor, I got a question to the bottom, to our mean error at learning steps. Why is the learning steps in the mean error so up and down, you know, why it looks like this?
Fluctuating. I mean, be aware the y-axis is logarithmically scaled.
Okay.
Okay.
Okay, thanks.
Okay. So this, yeah?
Yes.
Okay. So this still looks stable. And when you remember, we started with some 0.5 or so. So we still don't see instability. So this upper bound is quite safe. Okay. So I want to increase the learning rate now to 5, which might seem to be a bit absurd, right? But let's try. So I'm decreasing it now. So we look at individual updates. Yeah, that's good. Okay, first learning step. Second. Fifth learning step. All right. I continue. Oh, do you see what happens?
It's much bigger.
Yeah.
Yes.
This is the 11th or 12th learning step. After 12 iterations.
Yes. Oh.
I continue.
And
I
now
continue.
we have this.
We won't see anything I mean, we see something in the plot upside, but we are still in exponential growth, as you can see.
Yes.
This means exponential growth, divergence.
Yeah.
That's meant by a diverging learning rule. Okay, so it's gone. Okay, the numbers are kind of, I can't even read. So we have an exponent here. This is over 100 already. Okay, so this was part A. First, look at what's happening while we are learning. Then we played around with this learning rule alpha, which is critical for this algorithm. Yeah. So the approximation of this implicitly normalized Hebbian learning rule only works for learning rates which are small. The second part of part B of this exercise suggests that we are using a much larger data set. So we are using now 500 data points, and we have a variance of 10 and 50, and we again rotated to have a correlation in the data. So this was 500, right? This was 10 and this was 50. And this was 0.25 pi. That's the rotation angle. Okay. Much more crowded and much more elongated now. Here, look at the alpha. That's the alpha that guarantees convergence. Okay. So we do 100 learning steps because we have lots of data. I'm starting. Okay. That's a good starting point. So what we do now is, okay, after 100 updates of the weight vectors, we do see the result. Okay, and we see, well, the weight vectors are approaching the directions of the principal directions of the data distribution step by step. Okay.
Professor, I got a question. The difference it's between the example before and now the example, you change the data and make the size of 500. And can you tell me the difference between the data when you make it bigger and the data when it's smaller? What does that mean for the learning rate and for the weight? Can you explain me the difference, please?
So it doesn't necessarily, the number of training samples doesn't necessarily mean something to the upper bound.
Yeah.
Right?
Okay.
Because the covariance matrix, I mean, the more data you have, the higher is the confidence on the estimated statistical parameters, like the variance in each direction and the covariance of the directions with each other.
Okay. And what does that mean for the weight? Because you start now with 100 steps, and the difference between the example before and now, what's the difference?
I mean, the difference now is since we have the X and Y values now are much higher, right?
Yes.
So we are scattering, yeah. So, okay. Okay, the scatter of the data is like, so we have now 100 and 100, right? It's just an order of magnitude or 2 orders of magnitude higher, the values of x1 and x2 as we've seen it before. So we see larger eigen values of this matrix.
Okay, thank you.
All right. So I continue. As you probably see, the blue one already has reached the right direction, but the pink one is still needs some time to get there. So I'm just increasing the number of steps, of a number of updates till we look at the results. Okay.
It takes more time.
Okay, so we're almost done. So you don't see any changes in the blue one anymore, right? So all right, so now we won't see any changes in the pink one anymore. All right, so this is now a pretty small value of alpha, right? So we have 6 zeros after the dot. We can make it like, what did we do? We increased it. So I do 4. Okay. Okay, that's not a good, yeah, that's a good starting point. So we can also watch what's going to happen if we exceed the boundaries of stability. Oh, okay. So here we reached that point. Let's see. No, it's still stable. Yeah. So now we found the point where it became unstable. So as you can see, this is not, I mean, this happens really fast. Are there other questions? All right. So if
I had a doubt, like, so just a general doubt. So for perceptron, we had the label data. So
yes,
then we found the hyperplane, which separates the two classes of data. So here, our output of this learning is the weight vectors, right?
yeah, it's always
So-
the weight vector.
Okay.
Yeah.
So how do we apply this? So if a new data comes, what do we check with our learning data, like our learned weights?
This is I mean, this is a method to compress data, honestly, and we will see it. Therefore, I now want to move back. I want to go back to the slides, and we do yeah, the rationale behind it, which is principal component analysis. Okay.
Yeah. Okay. Yeah.
Yeah. Okay, because you see, there's another task, or there's another task on the problem set where you see we are working with some pricing data, and we want to have a consumer price index that best gives us a number for how expensive cities are. Yeah, there are all kinds of applications how you can use this PCA. So let me go back to the slides. Where are my slides? My slides are here. Hope this works. Do you see slides? Yes. Okay. So now we move a bit into multivariate data analysis and principal component analysis, because that's basically what we are doing with our linear network. So linear networks have strong connection to what's known as principal component analysis. And principal component analysis is basically a method to reduce the dimension of your data to the most relevant things. So what we are doing right now is we are now concentrating on networks that have actually fewer neurons than they have input dimensions, right? So because we want to reduce dimension. So this is a schematic view as you can look at it. So we have this covariance matrix, sigma or C. We call it sometimes CV, sometimes sigma. So this covariance matrix has k eigenvalues, right? And they are real positive numbers. So you can sort these eigenvalues, okay? And to each of these eigenvalues, there is an eigenvector. Okay? Okay, that's what this means, right? So if we select only the I eigenvectors that belong to the I largest eigenvalues, right? And project our original input space by a linear transformation using this eigenvectors into a so-called PCA space. So this is how we do dimension reduction. We just decide, okay, we are only interested in the first I directions of the data or eigenvalue directions of the data, and we project our original data onto this so-called PCA space. Or in other words, the PCA space consists of I principal components, which are the I directions in space that belong to the I largest eigenvalues. So what we know is that the components of the output vector y that we are getting, which is I-dimensional, are uncorrelated. And what we also know, or what we also know is doing this dimension reduction to a lower dimensional vector I by this linear transformation is that we are preserving a large share of the variance of the original data. We can put it the other way around. If we are doing this, we are minimizing the reconstruction error of the data, of the original data from this projection onto I linearly decorrelated outputs. So we have our weight matrix of our k neurons, right? So what we do, we have k inputs, we have the k neurons, each of them having a weight vector, and we put this into this weight matrix and we multiply our input data with the weight matrix, and so we get k outputs. But we are only using the first I of them. This is how you would implement it in a network. So the question is, why should we preserve the variance of the original data in this transformation? I mean, there's an assumption behind it. The assumption is that discriminating information, for example, for a class separation that you would like to do afterwards, right? That information to do this is basically included in the most varying features. Yeah. So strongly varying features give the most discriminative information for class separation. So this PCA pre-processing, so reducing the space, making a dimension reduction according to this PCA principle, delivers features that preserve the maximum variance in the data. There are some considerations that are related to this dimension reduction. So what we do to make this projection to a lower dimensional space, we slightly modify the notation of our weight matrix. Since we only have I weight vectors that we do need, we summarize them to a so-called, to a matrix W hat. Okay, so and the dimension reduction of the original data then is just done by multiplying all our input data with the transpose of this matrix W hat transposed. The vector y that we are the vector y is the images of the vectors x that we are getting under this linear transformation. They are vectors in I-dimensional space. So they are the projections of the original data onto this PCA space. So this is done basically, we have our input data, all the vectors x1 to xq. So we have a matrix which has dimensions k by q. Okay, so we have k inputs and we have q examples. So we do this projection using this matrix W hat, which has a dimension k times I. Yeah. So the transposed matrix has a dimension I times k. So, and then the dimensions here fit, just to make sure. Okay, and then we get lower dimensional output data, as you can see from the cube, right? So we get, for x1, we get a mapping to y1, which is lower in dimension. So we just have I rows here. So we have I-dimensional vectors. All right. So, and when we now use these I-dimensional vectors from PCA space, we can easily do a reprojection onto the original space by just transposing our weight matrix for this mapping. Remember, the eigenvectors are unit vectors and they are orthogonal to each other. So transposing means inverting the matrix, right? This is one of the properties that we did in the beginning of the lecture. So this is simple. So we can do a reprojection to the original space using this linear mapping. So this is the reconstructed error now has also a hat because it's not the one that we had originally, because we have done data reduction, so we lose some information, but we made sure that the loss of information is minimal, yeah, given the reconstruction error. So what we can say, we can compute the reconstruction error when we take the original data minus the reconstructed data. So this is the error, and this is the norm of the difference vector squared. Okay. So the reconstruction error represents the square distance between the original and reconstructed data. I'm considering this reconstruction error. So since we are reconstructing the original data from this I-dimensional PCA space, lower dimensional PCA space, the reconstruction error is inversely proportional to the total variance of the PCA space. So this is new. What is meant by the variance of the PCA space? I mean, we have the eigen vectors, right, that we are using to do the projection. But we have another information, that's the associated eigenvalue. And the variance is somehow, the variance is given by the eigen values. So if we are selecting a large number of principal components, so we are neglecting only a few of the low variance components, then we are increasing the variance in our PCA space. And we are decreasing in parallel the error between the reconstructed data and the original data. So when we understand this, we can talk about some robustness of the PCA. How robust is our dimension reduction? And we can control the number of the selected eigenvectors because it's not trivial to choose the right number I. And it depends a bit on the data, and we will see that there is a rationale how you choose I, how the dimension of your projection space. So what we know is that with each of the eigenvectors, there comes an eigenvalue. And we are selecting, or we do the projection using the eigenvectors that have large eigenvalues. The total variance of the projection space of the PCA space that's associated with the projection matrix W hat is given by the sum of the eigenvalues that belong to the eigenvectors in this matrix W hat. Okay, and so what we can do, we can compare the total variance of the PCA space with the total variance of the complete data set. The total variance of the complete data set is basically summing up the eigen values of all eigenvectors for the complete, the k-dimensional space. Or in other words, doing no dimension reduction. So the robustness of the lower dimensional space is basically given by the ratio of the summed variance of the PCA subspace in relation to the total variance of the original data. An application. So when we talked about the different principles of pattern processing in machine learning, there was an example where we want to compress images, right? And so what we will do now is we do a sort of loosey compression of images. We do this column-wise. So you can interpret an image as column data. So you take the column of the image, the pixel values of the image along a column, right? And take this as an input data. So this is a 512 by 512 image. So what we do have, this image can be interpreted as a training data sample that consists of 512 column vectors consisting of 512 data values, right? Next to it, we have another image. This is a 256 by 256 image. So in this case, we only have 256 data points, and they have a dimension of 256. So we have the Lena image and we have the cameraman image. Okay. So, and when we use these, now we are using these 512 training samples consisting of 512 dimensions. So K is 512. So we look at the compression or the compression results and the reconstruction error for different numbers of I. So if we only use the first eigenvector and eigenvalue, right? So we have a compression rate of compressed to uncompressed of 512 to 1, because we can calculate 512 eigenvectors, right? But we're just using one, the largest, the one associated with the largest variance in the data. So if we project now the original data, the original image, onto this PCA space consisting of just one dimension, right? We don't see much. The mean squared error, when we compare the reprojected, the reconstructed data with the original data, is large. It's 30. Okay. So the image in the middle is a reconstruction or is a reconstruction using 10% of the PC. So roughly 50, so the dimension of the PCA space is 50 eigenvectors. So we have a ratio of uncompressed to compressed given by 10 to 1. As you can see, I mean, the picture looks quite nice, but we do see it's not a perfect reconstruction, right? We lost some information. This is clearly visible. So the mean squared error of this reconstructed image is well below the one when we compare it to using just one principal component. So it's 5. And the right-hand side picture is we're projecting the 512 dimensional space to 50% of the principal components. So I'm not good at, I mean, it's like 256 dimensional space, and then we do the reconstruction. And as you can see, there is no difference visible between the original 500, the original image that's given here, and the reconstructed image from 256 dimensional PCA space. The same has been done for the cameraman picture. The dimension of original space K is 256, so we see the reconstruction based on the first component. And what you see, I mean, this is a bit better than what we saw from Lina. So at least even one principal component gives us a reconstruction of the image that shows some characteristic of the original one. If we go to 10% of the principal components, we see a pretty good reconstruction, right? But still some noise here, right? And again, if we use 50% of the PCs, of the principal components, to do the reconstruction, we see an almost perfect image.
Professor, I have a question, please.
Yep.
You say by the first picture on D, we say we cannot take the 256 eigenvalues because we cannot calculate with all of them. And in the second and the third picture, we take 10 eigenvalues and calculate, and the third we take two eigenvalues. This is right. I have a question because of the principal components. That means when I take more principal components.
These would be the weight vectors of our neural network that consists of 256 neurons. We have 256 weight vectors.
Yes.
Right? And the projection matrix W hat would contain just 10% of it, 25 or 26.
Ah, okay. This is my output. You mean like this?
Yeah, that's what we do. We do project it to PCA space, and then we can reproject. Yeah, we can reconstruct it using the transposed of the weight matrix because it's an orthogonal. It's an orthogonal matrix. So the inverse of orthogonal matrix, orthonormal matrix, it's transposed. That's what we really have done on the first problem set. All these kind of things. Okay. So this is all properties we are going to use. This is so basic. Okay. Yeah. And so we do this and reproject it to the original k-dimensional space. So we again have an image, right? And this is the image we get. Okay. All right. So the reconstruction error, what you typically see, these are the first, the first 100 eigenvalues for the first 100 eigenvectors of the covariance matrix in that data. So what you typically see, you see large eigenvalues up to a certain point, right? And then the size of the eigenvalues becomes smaller and smaller and smaller, right? So the amount of variance that's contained in these directions of space, this is marginal. So this is where we've been here, like 10%, right? So we cut here, right? And we neglected all the rest of the distribution, right? And so this is why this works. And usually what you see if you look at the size of the eigenvalues of a data set, of the covariance of a covariance matrix of a data set, you see this elbow. So you see significant size of eigenvalues up to a certain index, right? And then the rest of the eigenvalues are pretty small. And that's exactly where you would cut, where you say, okay, for a good compression, right, given a minimal reconstruction error, I can it's enough to use the first 10 dimensions of for PCA space, for the projection space. Questions?
Professor, I got a question, a last question. You say for the good compression, you say you have to use the first 10 dimensions of the PCA space. Can we check this on the photo? What you mean when you see it on the photo? This is the piece. Yes. Okay. Okay.
So it's a bit of a problem. I mean, for the linear image, we have 512 eigenvectors.
Yeah.
You have to be aware of, right? So this 100 is already only the first 100, right? So there are another 400 to come here.
Yes.
So if I would have plotted all of them, right, we wouldn't have seen anything here in the front.
Yes. Okay.
That's why this is a cut.
Can we see the slide before by Lena, I think, or by the man with the photo? Yes. By the first photo, we take the PCA space of 1. Yes.
Yeah, we are just using the first eigenvector.
Yes. Okay.
So PCA space is one-dimensional.
Yes. And when we want to get a good compression, we take the first 10 dimensions to get a good compression. Yes.
Yeah, I would say 10 to 20.
Yes. Then we get a good photo.
30.
Maybe.
That is.
Yes. Okay. Thank you.
All right. So let me briefly finish general remarks. So this PCA, basically what we are doing, we are calculating a set of new features, outputs, Ys. They are uncorrelated. Uncorrelatedness is defined in statistical terms as taking the expectation of the vectors xi times xi transposed in our data set minus the expectation value of xi times the expectation of xi, the same expectation value transposed. And if this is 0, we say they are uncorrelated. So PCA results in a set of uncorrelated data that's variance preserving, and it's one of the most frequently used dimension reduction techniques in the field of multivariate statistics and machine learning. This principle of variance maximization has some limitations. I mean, it works. I mean, that's the first thing you should try because it's so simple. But it has limitations. For example, what you are doing, so here we are looking the correlatedness or the covariance. It's the second moment of a distribution. And only if your data follows a Gaussian distribution, it's enough to consider the first and the second moment, right? Other distributions that are non-Gaussian, they are really poorly described by just mean and covariance. So you need higher moments, and you have to consider higher moments to get a good representation. So PCA is the most principal method of this kind of methods. There are other related methods which do have different acronyms. If you have, for example, labels associated with your data, you can do a so-called linear discriminant analysis. That's the next second complex analysis. So so there you look at, I mean, you are transforming your original data into new features, right? Which ensure that your classes become compact and the class centers are separated as most as they can, again, given covariance data. Yeah, this is also covariance based. Then there is a method called ICA, independent component analysis. ICA goes beyond uncorrelatedness. It ensures statistical independence. And there is also a method called SFA, which looks in the data for those components that are, this is a time series method. So you look for data that's changing very slowly. So because you think the noise data, the high frequency data in your time series is noise, okay? So these are more powerful criteria, and they are a bit more complicated even than what we did here. I mean, they're kind of really more complicated. So we won't dive into it. So just to give you the hint that there are other methods of this sort. But they have different objective criteria. Here we are basically maximizing or preserving the variance in the data and decorrelating the data. This was the last slide of this chapter. I know it's really complex, and there might be some questions that are coming up. I want to leave you with the explanation so far and give you some time to think it over. All right? You probably have to go through it. I will share a last two other slides. Not this one, this one. So we basically have the halftime break now, and the exam is scheduled to be in midst of February. Lectures stop the week before. So just to talk a bit about the examination and give you hints what's worth looking at and what's not part of the exam. So basically the lecture slides, the course material, the additional reading, the questionnaire, and the labs, these are the basis for the exam. But there are some topics that are unlikely to to show up in the exam. The first point is, for example, the detailed biochemistry of synaptic transmission, like the Nernst equation and what's going to happen when the transmitter or exactly which of the ions, the conductivity of which ions are changed when transmission between synapses or in synapses occurs. Okay, so in principle, what's covered by the videos we saw in the beginning of the lecture. Also not part of the exam will be the details on the organization of the visual cortex. Okay. What's also not part of the exam is the proof of the convergence theory. Right? You don't have to reproduce this proof. Okay. We also did a derivation and compared the single neuron with sigmoid transfer function to Bayes classification, and we calculated the weights and the bias based on the assumption of doing Bayes classification. Right? This is also not part of the exam. And what's also not part of the exam is proving the instability, not the stability, the instability of the plane Hebbian learning rule. This means the slides that are considering the system of partial differential equations. Okay. Are there any questions? I wanted to cover this before Christmas because some of you may want us to look at the slides and the content over Christmas vacation, so you don't spend too much time on the wrong material, right? Okay, so of course I wish you Merry Christmas. I know not all of you are celebrating Christmas, but anyway. Are there any questions remaining for today?
Ma'am, does the course material mean the book that you mentioned?
The audio was a bit broken, at least.
So yeah, I understood the lecture slides and the questionnaire and the lab. So the course material means the book that you refer.
Yeah, I mean there are dedicated chapters from the Christopher Bishop book, right?
Yeah.
And I also included a link to another book. But there I said, well, basically part one of this book covering the basics, the mathematical basics. This is additional reading. So because he goes through again to what we did very, very briefly in the first problem set in a quite extensive manner.
So like I don't know about others, but I have no much previous experience in this. So is it okay that we stick to your lecture slides and understand that?
Should stick to the lecture slides, right? And
okay.
You can look at the additional reading because there it's explained in length again, right?
Okay. So we can expect questions from the additional reading as well, right? Or
nothing that deviates too much from what's on the lecture slides.
okay.
Okay.
Thank you.
Okay. All right. Other questions? This is not a one-shot learning, to tell you right now. So this is not like you go once through the slides and then you well, I'm done. I got all of it. Okay. This is probably a 2 to 3 time cycling through topics. Yeah. Okay. So anyway, I wish you Merry Christmas. You deserved it. And yeah,
Yes.
see you
Yes.
after
Merry
Christmas.
Christmas.
And
Merry
I'm
Christmas,
probably we are
everyone.
actually continuing right after Christmas, but I will write a message in the to you when we continue.
Yes.
Probably in the first week of January. Yeah, because the exam is so close, right? So it's only a few days, so we cannot afford to, because I want to finish a week at least early or two. Yeah. Okay. Bye bye. Enjoy Christmas.
Merry Christmas. Bye.
Merry
Bye.
Christmas.
Merry Christmas.
Merry Christmas.